we're doing differences in means, so we're doing a hypothesis test today. So there's 4 steps. So what's the first step? Hypotheses. And we can compare these. We can compare these to 2 proportion z-tests. So if we're doing differences in proportions, and we're doing differences in means, what is our null hypothesis going to be?
mu1 minus mu2 equals 0.
Excellent. Yikes. Okay. So the alternative is that the difference is greater than or less than or not equal to 0, right? So again, we're showing there's a difference. The difference doesn't have to be 0, but a lot of the time it is. So then we have the conditions. It's your second step. You guys are getting pretty good at writing the conditions. It's the same conditions that we had yesterday with intervals. So let's go through those really quickly, just out loud. Independence. Group 1 members have to be independent of each other. Group 2 members have to be independent of each other. And the groups must be independent of each other, because you have 2 different groups. Questions about that? Randomization. Was randomization employed to get a sample from group 1? Randomization employed to get the sample for group 2? Again, don't put those together. Check them individually. 10% gets wishy-washy in this chapter, like we talked about yesterday. This doesn't make sense all the time. Like yesterday, we used an example where we had the number of days that a route was driven. So you start saying 20 is less than 10% of the number of days that the route could have been driven. That doesn't really make sense because the population is days instead of like a finite like number of people or something. So you can still check 10% if it's applicable. You'd say this group is less than 10% of whatever, and this group is less than 10% of whatever. Then the last condition is the nearly normal condition. So in that case, if you have all the data, you need to look at a plot of both groups individually to say that both groups satisfy the nearly normal condition. I understand that we have suggested using histograms. I guess you don't have to prefer, but I prefer to use a normal probability plot. Yes. A histogram in your calculator. The bar widths are based on an algorithm, okay? And so that algorithm makes it so that everything's nice and even and it fits in a nice little window and it all works, okay? You can change those widths to whatever you want them to be, though, and so then you can manipulate how it looks. So I don't necessarily trust histograms when you're looking at them in your calculator all the time, unless you have like lots of data. I'd prefer to use a normal probability plot because then you have a straight line or not, right? So then I can say, according to the normal probability plot, the data is roughly unimodal and symmetric, or is nearly normal. Like I can actually look at it and it's either straight or it's not straight, so I can make a decision. Or look at box plots, because box plots will show you how skewed it is. Okay, so be careful with histograms because those can be manipulated more than others. Does that make sense? Again, you need to check that for both groups of data. Questions about the condition? What's the next step? Mechanics. There are technically 3 steps to the mechanics and the hypothesis test. So what is the first thing you find in a hypothesis test? All right, the standard deviation or the standard error, depending on what information you have. In this case, are we going to have the population standard deviation? No, we're going to have the sample standard deviations, so we're actually finding the standard error. That's that formula we talked about yesterday. It's on the formula sheet. S squared over the sample size, S squared over sample size. After you find the standard error, what do you find? T. Like we would find Z before, right? We started with one sample T test, though, that we're going to be doing a T statistic. Again, it's always the statistic minus the parameter. So in this case, your T is equal to, what's our statistic in this case? Our parameter is mu1 and mu2. So what's our statistic? x bar 1, or y, our book uses y bar, x bar 2, minus mu 1 minus mu 2, but we're generally assuming the difference is 0, so this difference becomes 0. And we divide that by the standard deviation, or the standard error in this case. Right? That's what it says on the formula sheet. It says statistic minus parameter over standard deviation. Questions about how to calculate that? Then what would I find after that? After you have your statistic, what do you find? P-value. Now, in a perfect world, like in one sample t-test, how do we find the p-value? Right, so if we would like to do TCDF, what is TCDF going to need though? The degrees of freedom. Just like yesterday with intervals, we still can't find the degrees of freedom because there's this crazy complex formula, right? It's not just sample size minus 1 because there's 2 different sample sizes. Does that make sense? So, because of that, we can't do this. We have to do the test in the calculator, just like we did the interval in the calculator yesterday. Anybody want to guess what this test is called? A 2-sample t-test. You guys are getting so good at this. All right, so in your calculator, you would look up 2-sample t-test, and you would put in the information and ask for, and it'll give you, as an output, it'll give you the t statistic, and it'll give you the p-value. It will give you both. Okay? So we're going to have to use the calculator. Any questions about the mechanics, though? Very similar to what we've done before. So then what's the last step? A conclusion, and the conclusion hasn't changed. You still have to say the p-value is high or low. If it's high, you fail to reject. If it's low, you reject, and then you put it in context about what that means. There is evidence that, there is no evidence that. Questions about the general procedure? We good? So some many things to talk about, little things. We already talked about all this, we're good. We did 2 proportion z-tests. I made you pool all the data. Why did I make you pool everything in a 2 proportion z-test? What was the purpose? What did you assume in the null hypothesis in those tests? You assumed the difference was 0. So that means you assume that the proportions were the same. If you assume the proportions are the same, then you had to pool the data, because why would you have 2 different proportions in the standard deviation formula? If you said they were the same, they should be the same. So we pooled everything. With the 2-sample t-test, we don't know the standard deviation. We're estimating standard error. We don't know what's happening in the population. And we have to assume, like, the standard deviation equation is not based on the mean. Like in the proportion, the standard deviation equation was based on p. It was the square root of p times q over n plus the same p times q over n for the other group, right? So it was based on the proportion. Here, this is not based on the means. It's based on the standard deviations of the groups. So that means you have to add another condition if you're going to do this. If you're going to pool things, you would have to assume that the variances were equal. That's harder to show and harder to prove. So because of that, it's never wrong not to pool in this scenario. I suggest you don't pool in this scenario. The differences are really small, and the advantages aren't relevant enough or big enough to make a difference. All right? So you only have to pool on the 2 proportion z-tests in this class. You do not have to pool on these. You're going to be doing it in your calculator anyway, though, so you just tell it not to pull it. It's fine. All right. So that's one less thing to worry about here. So I've got two examples. One of them we don't really have to do anything, but the other one will do the hypothesis test. 21 says a company institutes an exercise break for its workers to see if this will improve job satisfaction as measured by a questionnaire that assesses worker satisfaction. Scores for 10 randomly selected workers before and after implementation of the exercise program are shown. The company wants to assess the effectiveness of the exercise program. Explain why you can't use the methods discussed in this chapter to do that. So why can we not do a 2-sample t-test for this set of information? Think about your condition. They're not independent. Right? If you're going to have independence, everyone in group 1 has to be independent of each other. Everyone in group 2 has to be independent of each other. We don't even have 2 groups here. We have 1 group. And then the groups have to be independent of each other. Here you have directly linked information. You have worker 1 who then took a question before and then after. Those are not independent responses. Does that make sense? Now, because of that, remember I said Unit 6 was 3 chapters, 23, 24, and 25. Well, 23 was on 1 sample t intervals and 1 sample t test. Chapter 24 is on 2 sample t intervals and 2 sample t tests. So theoretically, should we not be done with means? Should be. Except for, in the case of means, we also have instances like this where we have paired data. Right? Where you have one person or maybe you have twins or something. You have pairs of information that aren't independent of each other. And so because of that, in Chapter 25, we had 1 more set of tests and intervals for when you have paired information. Okay? Luckily, it's a lot like doing a 1-sample procedure, so it's not a whole lot different. But just know that's things you have to keep track of. If it doesn't meet the conditions, like if it doesn't meet independence, maybe you can't do a 2-sample procedure, but you can still do a paired procedure. Okay? All right, here's our example. Researchers investigated how the size of a bowl affects how much ice cream people tend to scoop when serving themselves. At an ice cream social, people were randomly given either a 17-ounce or a 34-ounce bowl, both large enough that they would not be filled to capacity. I would like to see them give me a bowl that I could fill infinitely with ice cream, because I would. They were then invited to scoop as much ice cream as they liked. Did the bowl size change the selected portion size? Here are the summaries. So you have small bowl, and they give you 3 pieces of information. Sample size, mean, standard deviation. Large bowl, sample size, mean, standard deviation. Right? Then it says, test an appropriate hypothesis and state your conclusions. Assume any assumptions and conditions that you cannot test are sufficiently satisfied to proceed. So that way they're just giving us an out when we can't check things. So, step 1, we have to write some hypotheses. We are writing hypotheses about the mean amount of ice cream put into the bowl, right? It doesn't matter which way you subtract. It really doesn't. But you have to choose. So we'd either do large bowl minus small bowl or small bowl minus large bowl. I want to do it the other way. Jacob, why do you have to make things negative? Every single time you choose, you make them negative. God, I think you like to do it on purpose. All right, then the question asks specifically, did the bowl size change the selected portion size? It doesn't say, did the large bowl cause there to be more ice cream or anything like that. It just says, did it change? So we say the alternative is, the difference is not equal to 0. Questions about that? Right, and since we're doing it in the calculator, that's going to do it for us. All right, second part is the conditions. So let's talk about them. Is everyone that got a small bowl independent of each other? Should be. Is everyone that got a large bowl independent of each other? Should be. Are the group of people that got the small bowls independent of the people that got the large bowls? Should be. So independent seems good. Were the people that got a small bowl randomly assigned to the small bowl? Yes. So then also they were randomly assigned to the large bowl. Does 10% apply here? Well, let's see. 26 is less than 10% of all people that could have gotten a small bowl. So it doesn't really apply, not applicable. Probably wouldn't check that. Sounds weird. Questions about 10%. All right, last one is the nearly normal condition. Do we have data or a graph to look at? No, we do not. We don't have all the raw data, so we can't make a graph. We don't have a graph. So that is why they gave us an out here in the textbook and said, assume any assumptions and conditions that you cannot test are sufficiently satisfied to proceed. So the nearly normal condition must be satisfied because they tell us it can be. All right? Because the conditions are met, we can perform a two-sample t-test. All right. So for the mechanics part, you are going to, since we have the information, we are going to write some of it out. Then you're going to do the rest of it in the calculator. But you are going to write it out so that you show what you're doing. You have to, on the AP exam, explain your thinking or explain what you're doing if you're going to use the calculator to do some final answer. So by showing what you can, it's showing that you know what you're talking about. And then it's okay that you use the calculator. If you just write the p-value and it comes out of thin air, they're not going to be happy about it. All right, so standard error. We have the standard deviation of the large bowl, so 2.91 squared, over the sample size, plus the standard deviation of the small bowl over the sample size. You can figure that out if you want to. I'm just going to leave it like that. I feel like I've sufficiently shown that I know how to find the standard error. For the t statistic, you have the difference in the means minus the difference in the population means over the standard error. So the difference in the means would be 6.58 minus 5.07 minus, we said that we think the population means have a difference of 0, so 0, over that standard error from up here. Again, you can write and figure that all out if you want to, but they're going to give you the t statistic in the calculator in like 2 seconds. So the last part would be to find the p-value. And yes, you would want to multiply by 2 if you could find the p-value by hand, but you can't. So in your calculator, it does it all for you. So let me show you. In your calculator, you go to Stat, Test. It lists all the tests before all the intervals, so you don't have to scroll through as much. So we're doing a 2-sample t-test. There is such thing as a 2-sample z-test. When would we use a z-test instead of a t-test if we had means? Only if you have the population standard deviations. If you have sigma, you can use z. All right? Does that happen? Not very often. So we're going to use t-test. It again has the data and the stats option. The data option, just like yesterday, if you had lists of data in your calculator, you could put in list 1 and list 2. We have statistics, did this earlier today, so you just type in the statistics from the information on the table. Make sure, since I chose to do large bowl minus small bowl, large bowl has to go first and small has to go second because it's going to subtract them in order, 1 minus 2. So don't do the opposite, you'll have the opposite of what you said you were going to have. Okay? So I typed in all the data. Everyone okay with that? Then you have to choose your hypothesis. Are you saying that they're not equal to each other? Are you saying one is less than or the one that's greater than? Okay, so you have to decide. We chose not equal to. It asks if you want to pool anything. The answer is going to be no. We're only pooling for 2 proportion z-tests in this class, so otherwise, no pooling. And then we hit calculate. It gives you the t statistic. So I know t was 2.103. And it gives you the p-value, 0.043. That's already been multiplied by 2 for you, because you chose not equal to. And then you need to report the degrees of freedom, because now we have some value. But we get all of the stuff in red out of the calculator. There is no other way to do that. You have to do it in the calculator. You have to use some sort of software to do that. Unless you want to do that huge long formula that I showed you yesterday. Questions about where those numbers came from? So the last thing would be to make a conclusion. Is the p-value high or low? Low. It doesn't give us an alpha level, so we'll say the p-value is lower than a reasonable significance level of 0.05. If it's low, what do? We reject the null hypothesis. So that means what? In this scenario. There is evidence that the bowl size changed the selected portion size. Notice I'm just restating the question just with the there is evidence or not evidence at the very beginning. Questions about what I just did? Questions about this type of hypothesis test? Again, it's getting fairly repetitive.